All right, so let's start. On today, we will talk about logical agents. As defined, basically, we've had agents so far which do things, right? But do they have knowledge? I mean, we humans, we have some sort of knowledge, and right? And when we do things, we generally do things based on that knowledge, right? At least we hope so, right? Sometimes, not particularly, we have some instincts, right? Urges, right, and so on. But still, yeah. But at least we are trying to build reasonable logical agents, right? So they will be based on some sort of internal knowledge base, right? There will be some sort of data, right? Or previous lectures, we had our search agents, right? Well, they did not really have full information. They didn't have a knowledge base internally, right? Here, the approach today's lecture, we will have an agent which will make an inference, meaning it will make some sort of choice based on internal knowledge, and also it will update this knowledge. So the basic idea is this, right? Basic idea is garbage comes in, garbage comes out, but no, basically, right, something, again, I'll do my paint, right? Something like this, basically, right? We're gonna basic idea is this: tell, ask, and tell. So basic idea of this, we will tell, right? Tell or perception, right? Tell or perception. Perception, meaning or sense or from our senses, right? Right? Ask, right? What action? What to do, basically. What WTF, what do I do, right? And basically, right? Perception from sensors, from senses or sensors, right? Right? And ask, given what you know, right? What to do, basically, right? And then we also have to tell. Last thing we have to do is what we did. What we did, basically, right? To the database, basically, knowledge base. So that's basic, really primitive way of what we did, right? So you have some sort of like KB, right? Knowledge base, basically, right? Right, 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 what to do, right, and what we did, basically, right? We asked, so then we did like a function stops, basically, on outcomes knowledge, basically, right? To do that, of course, we will need some way of internal representation of all this knowledge, right? So again, today we will look at some really basic logical ideas what to do, and then we'll see some limitations. Of course, it will not be perfect. Nothing is perfect, right? So maybe we'll move to some advanced logic. So for now, it is, of course, sort of like Boolean based, of course, right? But let's see again. I'll open up notebook. Do I have my notebook here? Yeah, I do. Where's my GitHub? Where's my GitHub? What happened? Oh, here you go. I'll open up code spaces, right? Shiny palm tree. Let's do it. So question is, what does knowledge base will contain? This knowledge base, what is it going to have? In this sort of AI language, we'll have sentences. So something kind of like our human sentences, right? So similar idea, right? Those sentences represent the knowledge, right? The form, of course, is pretty open-ended at the moment, right? So, right? So knowledge base, we already talked about this, right? So sentence, in this, the definition is it's a specific statements or assertions, right? That basically form the base, right? So facts, rules, relationships as well. What is bigger? What is in what? Maybe some set relations. Maybe again, we need, of course, come up with some syntax for this, right? So we'll need to have some formal language to encode this, right? So axiom. So what's an axiom? Again, you've probably again taken.
Like a theorem without a proof.
Yeah, it's sort of things like a self-given fact. It's like the base fact, basically, right? So who remembers Euclid's geometry, right? There are like some basic axioms, right? There's like 4 basic ones, and the 5th one is the kind of tricky one, right?
You can connect 2 dots with a line.
Yeah.
From 1 dot, you can like
Yeah.
base multiple lines. And there was a 3rd one
Yeah, but they're basically 4, like really 4 ones which can seem like obvious, and the 5th one is tricky one, right? They're both the parallel lines, right?
yeah.
Yeah, and the fact is the 5th one, if you don't take it, if you ignore it, you get a non-Euclidean geometry. You get a different Lobachevsky, right? Yeah.
Probably.
Yeah. So this is a big thing in 19th century, right? Because people are saying, okay, maybe we will need this 5th axiom, right? So axiom is basically true, right? Given. It's a fundamental truth, right? So like if you don't, so sometimes, by the way, it's interesting. Can you have a system where you don't have any axioms, right? When you don't have any starting facts? If you think about it, can you do it actually? Well,
Probably not.
well, it seems like you wouldn't, but the thing is actually, if you have a whole bunch of rules how to derive, right, you can sort of build on that actually as well, right? Maybe you need, of course, you think it's easier if you have at least one axiom, right, and you build on that, right? But yeah, if you have lots of rules, right, the rules, how you make these new knowledge, pieces of knowledge, these new sentences, basically, right? You have some axioms, right, and again, this all goes back to Euclid, right? His idea, right? You have these base things, and then you come up with theorems, right? You prove them basically, right? So inference, basically that's in the process of inference. That's what we're basically going to be doing, right? So again, we of course may have some background knowledge, right? Again, domain, maybe there might be some domain independent knowledge which is not related to anything specific you're solving, right? Some base things, right? So again. We have the implementation details, how we store the database. We're not going to talk too much about the implementation level today, right? Because what kind of database you use or what kind of storage, right? That's not really at the moment, not at the moment, right? Again, of course, it's important when you start making things, right? Of course, right? What kind of data structure you can use, right? What kind of maybe we'll get that far. Maybe we'll get to some things, right? So also because there is a sort of fight, right? Is it enough to declare knowledge, right? Again, those who've taken my programming language course, right? Prolog, right? Nobody has taken programming language. Some people are taking.
No,
We
You took Prolog.
Yes.
Yeah. So what?
I like that language.
You like so this is something like, again, so those who have know a little bit about Prolog, right? This is something like that, basically. So the idea was 70s, 80s, right? There was this idea that you could just declare knowledge, basically, right? And then you could infer it, right? You could come up with new theorems just based on this inference engine, right? Of course, the other camp was procedural, meaning, classical way of, do something. You have algorithms, implementations, right? You actually have to do something, right? Well, it turns out you really need both, really. Yeah, right? You really can't just, it's really hard to do everything purely declarative in Prolog, right? Making a really big application in Prolog would be painful, right? So, you probably remember, those who are still taking programming language will have that, right? So, kind of interesting, right? So, the book comes up with a really interesting example. Again, this basic world, right? A really basic world, 4x4 world, right? Called Wumpus world, right? There is a monster which eats, right? The agents, right? There are pits, basically holes, right? Also, of course, gold, of course, the reward, right? So you have some performance measures, right? So plus 1,000 if you get out alive with the gold, right? Also, you have negative 1,000 if you fall into pit or you get eaten by the Wumpus. Basically, the game ends, right? But also there's penalty, right? How your vacuum moves, right? -1 for each action, -10 for using the only available. You have an arrow. Let me show you the picture. Let me show you a picture. Where's my, okay, so that's what it looks like, right? This is from the book, right? So you start, that's you, right? Let me make this a little bigger. That's of course not you, it's your agent, right? And you have one single arrow, right? And you have sensors. But here's the issue, compared, unlike your homework, right? First homework. This one, you don't have the full knowledge of the world. You only start here. You don't know where the, so what do you see? Only surrounding area, right? Your sensors only look around the closest area, right? So that's how it is, of course, again. Driving taxi, right, doesn't have the full knowledge, right? You don't have the full knowledge of the world. So then you need some sort of reasoning engine to figure out where you can go, right? And assuming it's completely random, if you just throw things in this 4x4 world, right, you need to have one monster, this Wumpus, you have some 3 pits. So notice here, the Wumpus gives you what? Stench, it stinks, right? It's smelly. So 1, 2, 3, not diagonal, but only the neck close to the Wumpus you get stench. So if you move to the room with stench, like if I move to this room here, right, and I have stench, so what does it mean? I don't know about the Wumpus here, because the Wumpus could be here as well, right? Right? So if I go here, it's not given that it could be here as well, right? So if I go here, breeze means there could be a pit here or maybe a pit here, you don't know. But the Wumpus could be in a pit, it doesn't hurt Wumpus, right? It's a big monster. Right, and here, when you get to the gold, I mean, the gold doesn't smell apparently, right? But you get the gold and you have a breeze and stench. And if somebody put you in this, if you start here, right? Well, you actually, it's really, can you get out safely? Well, it's a toss of a coin basically, because you don't know where to go. It's 50-50 chance, yeah. You have 2 bad squares, well, you don't know basically. I mean, they could be all bad actually. I mean, it could be there's 3 pits around and on Wumpus and you're dead, right? Guaranteed, right? Or it could be Wumpus, maybe you have only 25% chance, right? You have to try something. But luckily you start here, right? I mean, and the thing is, if you start here, if there was a pit here, you will get breeze. If there is Wumpus here, you will get stench, right? So you're safe in the first, if you're here, in this particular version of the world, you're completely safe here, right? There's no sensor safe, you're okay. But as soon as you make one move, well, you'll be updating your knowledge, right? You have some knowledge base. And your only knowledge base at this moment here, right, is that, well, that one is safe. That's all you really know, right? You need to make, bless you, you need to make an action, of course, right? Of course, you could be asking your engine here to do, but we really don't have an engine at the moment, right? So, okay, where's my engine? Oh, there you go, right? So that's the world we're working with. Again, it's a really simplistic, right? But we'll try to construct a logical agent which can actually help us. Well, or hopefully help itself, right? Move around. Okay, am I recording this? I am recording, good. Now, what did we skip? Right, so stench, glitter. Glitter. Where the gold is, right, of course, yeah, you'll see but it's not near. Oh, by the way, okay, but to make the more interesting things, right, you can kill the Wumpus, right? But you get only one shot to do it, right? So you can shoot if you knew this is where the Wumpus is, right, you could shoot the arrow up, right? And it will kill the monster, right? But obviously, if you are here, you don't know whether to shoot up or right, right? So what's in general, what's the idea? You basically move, you update the knowledge base. Hopefully you get the inference engine will tell you what you should do, right? So if we are humans, right, assuming again, we would go here. If you go here, right, what should you do? Well, what should you, okay, you start here, right? Let's say you go to the right, you get the breeze. What should you do? I mean, yeah, back, of course, back, right? That's the only safe move, right? So you go back and go up, you get stench, right? So what do you do then? Yes, so you can go right. Why?
Because none of them have both.
Yes, okay, exactly, right? So you can see they're getting the idea, right? If you go here, right? This is how many card games, many logical games work, right? Kind of like we played Sudoku, right? So there's some logic here, right? So, stench, that means if this was a bad square, I would be getting breeze here, right? And here, I was not getting stench. So this means this square is safe to explore. So I will go here, right? And then, well, now because, okay, I don't know what to do. I go here, I get breeze. Okay, I'll probably go back, right? Because I don't know where the pit is, right? I have 66, in reality I only have, randomly I have 30% chance of surviving, right? If I toss a coin. So I go back where I know it's safe. I update the database, right? Knowledge base, right? And I go up here and I get my gold, right? And I backtrack and I go out and I'm happy, right? Right? And I'm rich and happy and safe and alive. Well, also, if I want to, I can kill the Wumpus just for heck of it, right? Because I know he's here, right? So you can actually kill him immediately, by the way, right? You could kill him. I don't know if it keeps stenching, right? Does it keep stenching? Does it have stinking? Does it keep stinking when it's dead? I forgot to check that actually, right? Right, so only one arrow, right? So very simple, right? But still leads to basically all of this stuff happens actually in a modern, driving car. So you need to represent this knowledge, right? A represents the agent, right? B is breeze. It's up to you, of course, how you decide this language, right? Obviously. And you also mark the squares. Okay, square, right? Pit, stench, visited, Wumpus, right? W, right? So when you visit, right, your agent's here, right? You basically mark it. Potential pit, right? Yeah. And then, of course, right, you go backtrack, of course, right? Because you don't want to risk it, right? You don't know, because this is your world, without cheating, right? Without looking at the map, right? This is the actual situation, right? So, okay. So you have none, right? None, breeze, none, basically here, right? You move to 1, you get the breeze. So let's see, five flags, basically. Let's see what is the flag here. Let me forget now. You have a breeze, stench. You could think of them as logical units. Yes or no, right? So idea is to come up with some language for this, right? Some syntax, right? So, because, for example, let's say if you take arithmetic, right? X plus y is 4, right? We know what that means. But if you have, right, x, 4, y plus or something, that's not really a language we know. We don't use that, right? So we need something to represent that, right? So, there's a fundamental concept called entitlement, right? Logical entitlement, but entailment, right? But kind of similar idea, entitlement, right? So basically, there's a set of premises, right? As probably the most famous one is about Socrates, right? All men are human. Socrates is human, right? I mean, all men are mortal. Socrates is a man, right? And of course, it means Socrates is mortal. He's gonna die, right? Drink his hemlock, right? So now his poison. So that's the idea, right? That you have the entailment is some set of knowledge. Basically, a new sentence can be generated. It's a conclusion, basically, right? So idea is that you need a sound inference algorithm, right? Meaning the new sentences, right, which are produced by this, right, only they have to follow logically, right? You don't want to follow, random sentences, obviously, right? New truths without, actually it's not really truth, right? It does not follow logically, basically, right? So completeness, another property, right? So the algorithm should be able to derive any sentence that is actually possible, basically, right? So of course it's infinite in most cases, right? All the possibilities might be infinite, right? So you need a complete procedure. You can make all valid inferences, right? So you can make all valid inference can be, right? So, of course, then you have the concept of grounding, right? Again, we're talking, so this sort of like this abstract world, right? We need some way of actually grounding this into a real world representation. So that's the basic idea, right? So sentence, right? From sentence, right? That's a representation. Underneath you have, of course, the real world, right? Okay. I mean, again, I think it's all common sense, but there might be something not so good. So this is the first simple logical system, right? We'll use only a couple of propositions, right? How we're going to use them? Basically, we're going to have atomic sentences, right? So each symbol represents something which is true or false. That's it, right? Only truthsy or falsy, right? We have symbols, letters. That's our syntax. Numbers, right? Again, idea is, of course, to use something that, to represent some mnemonic, right? To represent what we are talking about, right? East, west, and so on, right? To help you actually make sense of what you are talking about, right? Just like we use variables in regular programming, to make sense, right? No point using A for apple. Well, A for apple is okay, I guess, right? But, A for banana is kind of bad, right? Right? So, again, same thing here, right? Again, this is not full programming. It's not a full program line. It's not prologue. It's not prologue, right? It's before. It's like you could say a proto-prologue, right? So, we have proposition symbols, true or false, right? And basically, you make these complex sentences by combining simpler sentences, right? So you can use parentheses, those are allowed, or these logical operations, right? And, or negation, those three you probably all know, right? But there are two more. In this specific logical system, there are two more. You'll be using the implication. So what's implication? So again, negation, you all know. Negation, reverse the truthness, right? Simple. Conjunction?
Close.
Yeah. Disjunction? Or, right?
Mm-hmm.
So implication. So the truth table for implication. Let me show you the truth table for implication. And implication, Wikipedia, or Boolean algebra, right? Boolean logic, right? Same thing, right? All right. Boolean implication. I don't want Stack Overflow. There's no need to complicate things, right? It's here. Yeah. So that's a truth table. So look at this. Yeah. So from P follows Q. So what does this mean, right? So notice something else. It's interesting. Why it's not quite like our usual implication. Notice what's here. If P is false, right? This is fine. Q can be anything. If P is basically what this means, if P is bad or non-existent or false, right? Q, right, could be 0 or 1, right? Because this implication does not provide any additional information, right? If P, you cannot have a sentence. I mean that if it's true, right, it cannot be false. The Q cannot be false. So this, of course, if P is true, Q is true as well, right? So that's a truth table for this implication, basically. Now, there's one more, and it's equivalence, or they call this biconditional representation, meaning, here, I have truth table, okay, yeah. I copied the book information here. Okay, so negation is easy, right? P and Q, right? P and Q, right? P or Q, right? And so this is, look at this one here, equivalence, right? So this part is here true only if both are same, if both are false, or both are true. By the way, what's the opposite of this one? Do anyone know? It's not in this logical syntax, but there's one more. Which one? Do you know? What's the opposite? Basically, if you negate this part here, which one? Do you know?
We should.
You should.
We should.
Yes, exclusive or, right? Because it's false. right, if both are false, and it's also false if both are true. And it's true if only one of them is true, right? So XOR is a negation of this equivalence, right? Them equal, basically, right? So those are our rules of combining facts, right? For combining sentences, right? Right? So simple stuff, right? Okay. And we can, of course, again, those who remember programming languages, we could come up with a EBNF grammar for this, right? Some people have bad memories. Some people still doing homework on that, right? Right. So, yeah. So yeah, that's a grammar. Again, I'm not gonna. Again, it's pretty self-explanatory, right? But you can see, of course, that's all what's allowed, right? But of course, that covers only syntax, right? It doesn't say how it works, right? Right. So, it doesn't say that's how it works. No, that's syntax, right? Now, how about semantics? Right. So that's a little hard to say. What does it mean? Sort of, in a common sense way, it seems pretty self-evident what we do, right? So, yeah, we define our facts, right, and then we basically sort of check, right? So, we assign truth or false to each symbol, right? And then, of course, we compute them, right? We have the rules in place. It is pretty easy to compute, right? So, all right. So, assuming we have started with some of these atomic pieces of knowledge have some truth or false values, right? Of course, we can compute, right? Pretty easy, right? Yeah, right. So since all sentences are computed constructed from atomic sentence, right? So how do we calculate, right? Atomic sentence directly, truth or false, right? Yeah, right. So again, each connective, affects how to form it, right? So we can use these truth tables to compute, of course, right? Right. So, but of course, when you get to truth tables, right? So, let me see if I can write this here, right? Negation, right? Right. These we already saw these. This is actually we saw it already here, right? So, how about using this knowledge base, right, to represent this Wumpus world, right? Because again, the goal is to come up with some sort of inference which should tell us, hopefully, right, whether it's safe to go, right? Because then, again, we don't want to, we could come up, of course, with our own informal way of like some if statements, something, right? Sort of, but it's kind of painful, actually, right, in general case, because we don't know how many, how big the world is going to be, right? We want to have it, this grounded, sort of this logical way of approaching this, right? So, we encode this knowledge. So we encode facts, right, in our knowledge base, right? So knowledge base will basically be, some state structure which will include all these logical sentences, right? Again, very easy to do in Prolog, of course, right? But again, Prolog is like an overkill for this right now, right? So our syntax, right? Of course, initially, we don't include what the agent is going to do, right? Not yet, right? Later on, we will be actually moving and updating the database. Right now, it's sort of, we just have the starting initial state, basically, right? Again, I think it's all pretty commonplace. Right? You need some way of encoding it, and you need some way of updating this knowledge base. So far, so good, right? Okay, right. So again, so here's how it's done. In this particular case, and in this version, right, pxy, x comma y underscore, right, says it's a fact about the world that there is a pit in xy, right? Where's my? Let me see if I can. Let me screenshot this Wumpus world so I can go back to it. We'll open up a new. Can I download this? Yeah, I can. I think download. No. Oh no, there it is. Okay, it's actually here. Follow link. Yeah, there you go. All right. Yeah. So one thing about this chapter, it's interesting because it's going very slowly, right? That it actually, which might seem like kind of weird, the facts are encoded for each square here, right? Where it's going to show you here, right? So this part here, right? It is atomic in a sense that, where's my Wumpus world, right? That if I say pit 1 1 is false, right? That the encoding is done actually here. Let me do a paint, right? Yeah. So something like this. So pit 1 1, right? Now I'll try false, right? Equals false, right? Because we know there's no pit, right, in the beginning, right? So this is one symbol basically, right? These are not variables or anything like that in this system, right? So these are basically just one. It's just like one name basically, right? Again, very kind of like really awkward way of doing it because you see why this is leading to the problems, right? It's going to be hugely inefficient for a large world, right? Because you have these variables like A1, A2, A3, A4, it's kind of the same problem, right? You encode it like a, like encoding, you'll have a real encoding problem, right? So, where are we here, right? Okay, so again, same thing for Wumpus. So you have 5 different type of facts, but basically they're all, of course, rolled as squares, right? B is true, right? S is true. G is gold, L is agent, well you could use A, right? So, and we can of course label it, right? So these are facts basically, right? Let me see about these facts. Let's see if these facts are actually normal, correct. Like so, a reference, each sentence. So, welcome back. So, B11, right? Is same, yeah, it makes sense. By the way, look at this, right? This fact, this sentence, right? So, let me do it again. So, so what is this? What are we saying here essentially? How are we encoding this fact? If there is so breeze at 1 1 is equivalent to pit being on 1 2 or 2 1. We all agree on that, right? That makes kind of complete sense, right? In this world, if there was a breeze when we start on our starting point, right? There. Where's my breeze? Where's my Wumpus world? Come on, I lost it again. I had it. Maybe I used different picture. No. I'll put here. Okay, yeah. Right, so how about this fact? If there's breeze here initially, right? So 2 1, right? This means 1 1, 2 2, 3 1, right? So we can encode this information basically, right? Right? So R1. So this is a reference, right? So, but we need some more information about this world, right? So how do we encode that Wumpus is in 1 square, right? We can say this in 4 sentences. Let's see if this is correct. Truth, right? But this is just 4 different sentences, right? Right. The only thing, but let me check if this is actually completely correct, right? So how do we encode the fact that there's 1 Wumpus, right? It's kind of painful, right? So we can say, okay, it's either here, either here, either here, either here, right? Makes sense, right? So again, these are not variables. These are just names, basically, right? So basically, the logic on variables will be next chapter, not today, right? So we can generate a truth table, right, for this, right? Basically, right? Yeah. So, how we can use this truth table to come up with this knowledge, basically, right? Right. So basically, is there a pit in 1 2, right? So, inference. So 1, 2 in right hand column, yeah, so true, 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 right. So we want to have the when all 5 reference facts, let me see what we have, R1, 5, R5, right, yeah, so pit, right. So basically, the only time, only 3 places, only 3 of these possible conditions, right? There is actually pit. There's no pit, basically, right? So let me see this. If I can explain how this works, it's kind of painful, actually, right? So P1, 2. Let me see. 1, 2. All 3 in just 3 of the rows, right? P1 is 2 false, so there is no pit in 1, 2, right? Of course, it does not mean that 2, 2 is safe, right? So we can safely advance to this 1, 2 because, again, in this particular case, if these sentences are true, right, then it actually means that there is actually, right, there's no how should I say, no pit, basically, yeah. So the question is, of course, so to verify if not, right, not pit at the location. So we basically could check this truth table, right? So, and basically the problem, but here's the problem, right? As your knowledge facts grow, it becomes exponential, basically, right? So that's a big problem. Is this? It's a big limitation of this approach, basically, how to prove problems, basically, right? 2 to the n, basically. Your facts grow, right? It's basically your approach, your model checking, right? Anything will be exponential, basically. So this is really, really not efficient, right? So we'll need some better way of proving it, basically, right? So we would like to use a model instead of using these truth tables, actually, right? To check how do we prove, how do we perform inference, right? So one of the key concepts how do you prove theorems is, of course, 2 sentences are equal, right? Facts, right? If the same truth value in every model, right? No matter what you plug in, it will come out true, right? So no matter what you plug in the values, right? And again, you're plugging in true and false, right? But you have to come up with the same truth values no matter what you do, right? So a tautology, right? What's tautology?
Repeating.
Do you mean?
Repeating. No?
Yeah, a tautology is something like a self-evident fact, basically, right? It's like, x equals x, right? Something is completely, it doesn't matter what you do, right? It's always same, right? Basically, right? So, sentence is satisfiability. A sentence is that's an important concept, right? So there's something called SAT problems. Basically, whether there is a model where you can plug in the values, true or false values, right? Something like, right? Can you, for example, right? Let me give you an example sentence, right? Paint. I'll do another paint, right? So something like this, right? You have like, I don't know, right? A, I don't know, something like B, I don't know, B, where, or maybe not, right? Not C, right? And I don't know, C, Control Z, name, yeah, and I don't know, B, right? Again, right? On is this. Can you give me some truth values, right? True. Can you do true here? Well, I think it should be easy because you have only 3 variables. Let's see. Can we get this true? Can you satisfy this sentence? Let's see. This is true. I think it's so easy here. We can plug in A is true, no problem, right? That works, because if A or B is true, you don't care about C or B, right? So this is like trivially, almost hard to find false. Let's see, can we get it false? False, false. Then true. Yeah, we can get something false here at this end here, right? Yeah. So we can get something like it's almost hard to get false and true. Yeah. So in this case, it's almost easy. It's almost trivially satisfiable sentence, right? So let's look at one of the major ways of proving things, right? So there's some rules, right? Again, you might have seen these, right? So modus ponens, probably the most, right? These are the basically logical rules, right? Yeah, you know how you can make one logical transfer to other. You had the course on logic maybe somewhere?
Yes,
Yeah.
we had in logic
Discrete
discrete
structures.
math.
Oh, okay, super. You're in good shape actually. So modus ponens also nothing new to you guys, right? So okay, so basically this chapter is sort of like a refresher. Very awesome. So modus ponens is like probably one of the most common way of inference, right? So basically this is how you write it, right? A, right? You have fact A is true, and you also have inference rule. From A follows B, right? Or beta from alpha follows beta in this case, right? But that means, of course, that beta is true, right? Premise, two premises and a conclusion, right? So very famous rule. There's also AND emulation, right? You can, if N and B, right? We can. So if you have this, so AND elimination. If you have a fact like, this is AND elimination, right? Right. Oops. What the heck? Right. On this, I'm going, true. What does this mean, right? This means that A is true, right, and B is true, right? Right? That equals true, right? Because otherwise it would not work, right? Yeah, and so on. So basically a bunch of these rules, right? So you can see, of course, computers really love this stuff because it's easy to encode, right? They just chew it up. Right? Humans have a harder time. We at some moment, 6, 7 levels deep, we'll start, sort of like spacing out, right? Yeah. Right. So, all right. So how do you say these rules are sound? Of course, again, because if you consider all the possible truth values, basically, right? You check, right? You plug in the values, all the possibilities, and does it work or not, right? So you don't want to have a false conclusion, right? If you have premise true, right? You won't have a true. So one thing is mentioned, of course, right? Not everything is both ways, right? If from A follows B and you have no A, right? You get B, right? But if you know from A follows B and you know B, not necessarily, right? A is true, right? So, good old question: do wet streets cause rain, basically, right? Or like right now outside, or does rain cause wet streets? That's a good question, right? So, what else do we need when we're using these models, right? So, again, we need some good, better, bigger inference algorithms. One of the approach is, of course, right, so some rules, right, how to resolve a larger sentence, basically, right? We want to probably, one of the things we use is something called conjunctive normal form, right? I don't know, you did this conjunctive normal form? Yeah. You got transfer, right? Okay, then you'll remember this, right? So where is my conjunctive? Yeah, so CNF, right? So you can convert any propositional sentence into this normal form, right? And why do you want to convert it? Because, of course, then the computer will know how to work with it, right? So we need to have a conjunctions. This is basically means that we start out with some general sentence, right? And we end up with and, basically, right? Right? If I remember correctly, like if I, let me look it up. Conjunctive normal form, right? Yep. Looks like something like this, indeed, right? So this means that the last action is conjunction, right? So of course, right, so this is not conjunction, right? Because not is the last one. This is also not, because or, right? Not, right? So also not conjunctive because and is netted within an or. So let's see if we can convert this one here, right? Oh, everything should be in so this is, so can we convert this? This third one, right? Or actually we can convert, let's start with A and B, right? We want to convert this to equivalent, right? Maybe somebody remembers this. So this is not, so this is not conjunctive A and B, right? So how do we convert this to, so again, for humans, if you haven't done this for a while, we need some sort of little brain movement. So we want to end up with something which is and, you know, something like this basically we want to end up, right? Potentially, you know, right. So can we come up with some, we can do it, right? So who can give me an answer, who remembers? Not A and B, all right? We are allowed to reuse B's and A's, by the way, right? We are able to, we can split them out, right? So what does it mean? We can, of course, use truth tables. Yeah. Anybody have any idea? Of course, we enter ChatGPT, of course, will do it for us, right? Sometimes it's
A not B and B not A.
okay.
Like
A
conjunction B.
A or B? No. Okay, what does it say? This means it says essentially.
We can draw.
Okay, we can do, of course, truth tables basically.
We can also draw this weird diagram, Lens diagram.
Yeah, you mean, so yeah. So what do you mean? Do you want to draw like this?
And then B, like overlapping.
Yes. Okay. So we are looking at this area, right? Right? It- yeah.
Yes. Yes. Mhm.
Okay. That's what we are looking at. How do we represent this with that? And we want the last action to be at. So not no.
Not A and not B.
Or maybe not A or not B.
Mhm.
Could it be? I'm just guessing. Could it be like this? I don't know. Not A or not B. No, I don't know. Okay, we can draw two tables for this, and then we can come up with this basically, right? So the truth tables for there are those are basically 0, right? A, B, right? 0, 0, 1, right? 1, 0, 1, 1, right?
You will need the 4 conjunctions instead of.
4, we need one more, okay.
Yes.
Okay. You come up with what's, can you give it me? Because I'm like that.
Well,
So, because it's really 4, right? Maybe, I mean, maybe possibly, right? So what are the,
if you finish the truth table, then you can for each row
yeah,
calculate the.
that's one way, that's one approach, right? Come on. So, truth table, oh, come on, why can't I type today? Why can't I draw? What's this? Oh, yeah, there we go. Oh, wait, okay. So, the truths. If get this means that
So the first one will be 1,
1, yes, okay.
0, that's right.
0?
No, actually, 1, 1, 1, 1, 1. 3 ones and
Yes, that's what I thought, okay. Review. 3 ones and then 0, yeah, that's it. Okay, so we can, yeah, okay, we can basically say and, right? No. But remember, we can't put or. It's easier to be disjunctive, easier, right? We can say, okay, either not A or not B, right? Or A and B, right? So, yeah, okay. So how, let's do this. So, you had a solution.
well, I didn't finish it, but.
Okay, so we have a truth table. And what's next to do this?
Break all the ones that leads to one.
Yeah, that would be one day doing. And. Right.
Well, for each row, you think of the logical proposition.
Mhm.
In the first case, it should be not A or not B, I think.
But the thing is, okay, so here's the thing, here's the problem. Because you see, we want conjunction on disjunction. Disjunction is easy, right? Disjunction is easy to generate. But we want conjunctive. You mean the truth table? Oh, correct, this looks okay. Truth table looks okay, because, right?
No, it's good.
Truth table is correct. Because if it's 1, 1, it's 0. Otherwise, it will be reversed, right?
The diagram is slightly correct, but also
Diagram is correct?
everything outside the circles is also true.
Oh, yes. Very good point. So we'll add this as well. Oh, come on, Rickard. That's also true, right? This is our world, right? So, okay. How do we combine it? You see, there's procedure. Like, of course, I can look up in the book, right? That might be a way of doing it, right? How to do it? So, conversion algorithm. Let's see. Basic algorithm. Okay, here. Okay, we can look it up in Wikipedia, of course, right? Disjunctive. Okay, this is easy. This is the part. Is the easy part. This I can do, right? So let's do that. Then you negate, and then dominants remove all dominant. Oh, God,
That's a lot of.
you had to do this, right? You were forced to do this, right?
We were.
All right. So basically, maybe I won't torture you because you already been tortured enough, right? But because the computer can do it, you trust me, the computer can do this because it's all straightforward and there's no, But yeah, but here, where are we? Here, right? Basically, so first we create a disjunctive DNF, right? First, and this step I can show you, right? We basically do yes. Right? It should be not A and not B, right? That's one. Or not A and B, right? And then we can do this, right? And again we do this, right? And of course, finally, A and not B, right? And that's it. One of these cases, right? So that part is easy. Disjunctive, right? But then you have to do some conversions. I thought it would be easier. And. Because it's like there should be an easy way to do it. Maybe I'm okay, but again, the reason it does because once you get this form, right, the inference you can do, it makes things easier for resolution, basically, right? Yeah. Right. So, okay. Now let's see what else we have left, right? So resolution algorithm, right? Right. On the this horn clause, right? So horn clauses are basically disjunctions of literals, is at most one positive literal, right? So let me see a horn clause. Let me show you. You probably had those as well, right? Horn clause. Yeah. Disjunction form, right? Assume fact, right? Okay, so the horn clause is the disjunctive clause. It contains at most one unnegated literal, basically, right? Again, so because if you have, why do you want this? Because if you have two clauses, right, basically it's gonna turn into one clause, basically, right? So you can resolve it basically in logic programming, right? So basically you can write it like this, basically, right? Prolog uses it underneath its engine, right? Because again, if you think about how does the Prolog actually solve, I mean, if you give it all these facts, right, it needs to come up with some solution. Let's see again. So, given we have some time, I want to show you, maybe you can get actually something practical. So, right, we construct our sentences, right, and we have a way of checking whether something is true or not, right, basically. Backward chaining, right, we can use check something, whether actually, check or answer, basically, whether it can be answered or not. All right, backtracking algorithms, right, so there are different ways of checking these. So again, in general, this is a hard problem, meaning NP hard, right, you can't, in general, fact world, right, you can't find everything about the world, right, but there are different search algorithms for finding, searching SST problems, right. Now, let's see about actually maybe testing some things, right? So thing is, in general, right, this is really hard, but many sentences, right, these SAT problems are actually easy, turns out, right? So there's some problems in the middle, right, which are really hard, right? But some are not so hard. So, you have this type of engine, right? Again, we didn't go into all the dirty details, right? Again, the engine converts them into normal forms, right? Again, it should be good enough to generate this, checking these facts. Basically, now you can apply it. You plug it into the Wumpus, right? Into your agent, right? And you deduce. You give it the original state, right? You say what you're going to do. That updates the truth values, right? And you can always get the best information that's possible from this world, right? Again, using the approach I mentioned in the first slide. Tell, ask, and tell again what we did. Tell what we have, right? This goes in knowledge base. You have inference engine here, right? Tells you what to do, and then you tell that you actually did it, right? Because maybe you said, okay, I don't want to do it. I did something else, right? It's possible, right? Maybe you have competing engines. I mean, it's possible to do some hybrid approach, right? Because if it's a big world, right, you probably have multiple knowledge bases, right? You don't want to have one unified one, right? I mean, it's possible you say, okay, you told me not to go there. I did anyways, and I fall into, from a cliff, right? So, now, you need to track the world state, right? Logical inference, right? Again, the interesting point, of course, they did some experiments, maybe you could do it too, whether all of the world, assuming they're all random, right? Are they all solvable? I believe it was proven already like in the 1970s for such a simple world, if you just randomly toss the Wumpus on the pits, right? I think about 30% were just you were dead anyways, basically, right? So yeah, and so you could test yourself, right? A little program in Python and check whether actually you have some bad, Wumpus and pit and you're dead, right? You can't do anything, right? I mean, thing is, okay, if you have Wumpus and pit, well, you can just leave, right? You can always leave, right? And you don't get the gold, right? So. Again, so you can imagine, of course, you have 8 pits, right? Of course, there's no way to solve it, right? But this is sort of like a middle ground, right? So, right. Now, again, so hybrid agent, right? Right. It needs to make, it may have a search, regular search, right? Right. But it also needs to deduce these various what's happening, basically, right? So again, you keep updating the knowledge base, right? And you make inference. Let's see if you can build a I want to actually do this actually in practical sense. Again, it's all theoretical, right? Let's do actually this in practical. We need some sort of, again, let's use some built-in library. Oh, come on, restart. I need to actually do something, I guess. I was not doing anything enough. An hour? No, more over an hour. All right. I believe there was I didn't test it last time I did this, but there should be a library which we can use now in Python, of course, as well, right? So we go to our Wumpus. Let's see if we can represent it. All right. So all this is all nice theoretical, but I would like to actually do it in practical sense. All right, and I think, okay, there are lots of algorithms for solving this, right? Propositional logic, all good stuff, right? All the history of all of this, right? But let's see if we can get this lib logic, right? And let's see, this is actually a language. And let's see. Formula. Propositional logic library. Right. So that's a library. Of course, it's easy because, of course, you can define some logic. So question, did I actually, I think I imported it. Yeah, I think I did. Let's take a look how I did it. From liblogic, I see, oh, here it is. Oh, it's here. Oh, yeah. There it is, right? So let's import some atomic facts, right? So, formula, atom A, B, C, right? And we can basically use these facts. Let's take a look what happens here. So, formula A or B, right? Valuation for A true. Another example, set nothing, no counterexample, right? Formula A from A follows to B, right? So, counterexample would be A or B, valuation, right? So let's see DOP. So what is so counterexample? It's transition, right? Let's see F, right? We supply this formula basically F. Right, and then we actually define, okay, these are all atoms, and E is, what is that?
It's a vending machine.
Oh, vending machine, okay. Is it going to give us free stuff? No? Oh. You want to, somebody want to check it out? Maybe it's giving us free candy? No. All right. So, let me see this library. It's kind of simple library, right? 13 years ago. Maybe this is actually written for the book, I believe, or one of the books are using it. So, tautology. Oh yeah. So you can see actually gets actually kind of complicated in the moment. So let's see. Let's see if we can add to our Wumpus facts about the world, right? Let's clear the facts. Let's add some facts about our Wumpus world, right? We will use, yeah, let's see. So, pit, XY, right? Wumpus, breeze, sky, so this should be doable, right? Goal. So what we have 5, and that's it. Agent, hunter. Okay, hunter, all right. And hunter is facing. Yeah, that also is needed, by the way, right? So 3, 6, 7 different facts, but of course, that is 7 times 16, right? Because we have 16 squares, right? That is 112? Yeah, 112, I think, right? Or am I completely not right? 7 times 16 is 112, right?
Yes.
Okay. All right. So, logical connections, right? Yeah, of course, those, right? And or not implies equivalent. I don't know. I think it's using different ones, right? Actually, it's using this one here, all right? Right. Implies this one, right? using emojis, right? These are not emojis, but Unicode. On negation, we have negation. We have negation command. Maybe the negation command as well, right? For oh no, it's correct. R shift, no. Left shift, no. That's not it. Let's look at this library again. Oh yeah, so that's negation. We need that. Do we have following? Does this follows or does this actually? Let's double check. And or implies. Okay, yeah, it implies. Okay, implies. Okay, right shift, left. Okay, yeah. If. Okay, all right. That's actually correct. So again, AI is correct. I was wrong. All right. Yeah, we need to use this. Implies, right? And this will be right. So why is it? Because of course implies we are overloading this right shift operator, right? Right shift operator. Yeah. We are over left shift. We are overloading this left shift operator, right? Not binary, right? Okay. Now let's take a look at some facts. Let's encode. No, we need to encode the world. Equivalent, right? Right. Well, that's fine. That's correct. That's correct. Now let's do encode the world, right? Logical axioms, right? If there's a pit, well, breeze is not really. If there's a pit, do you have? Well, that's kind of obvious one, right? It's not. That's okay, but that's kind of it's too late. You see, it's not so well, but that's not correct, right? Logical rules. No, we want to encode. Let's encode the world, right? Let's encode the world. Let's encode the world. So it's going to keep. Yeah, we saw. So let's encode it. So atom, right? P12, right? 11 atom P11, right? Right, and so on and so on. So basically, so you have to encode all 16. You would have to encode 7 times 4. How many atoms? 112. Okay, it knows math, at least. That's good to know. Right. So and so on, right? And so on, and so on. Wumpus 1, right? And so. Okay, maybe let's do smaller. Instead, let's do smaller. Instead, let's encode. 2 by 2, right? 4 atoms, right? And so. Right. But of course, do we want to encode this? Or we don't want to have 4 pits, right? So let's encode. We don't have any knowledge, right? Atom, hunter, atom, right? And so on, basically. We could encode, fires, and so on, and so on, and so on. And we could encode it and all get the resolution. Right. So, let's see how we could we do this basically. Maybe let's see if could we come up with our own navigator logic for this actually, right? Human logic, because again I won't have time to encode those cells, right? So, well, probably not enough in a couple of minutes, right? But so our pseudo-code, right? Right. Build initial state world. And well, right. Action of the world, right? Add rules about the world, and then send the world to the logic unit to get the results, right, of or ask or queries, right? Perform action, perform query on inform knowledge base of the new facts, right? And that's basically it, right? So you could write pseudocode, right? So leave magic here, right? So we can write this, define build initial state, right? Initial state, right? Facts, right? Pass, right? And then, you know, ask or tail, or should I say tail? Right, tail, right? Percept. Ask. Well, that's tail action, right? Well, that's afterwards. But, and of course, define tail. Yeah. Tail, ask action, right, pass. This would get you action take, right? And of course, so this, and you keep doing it, and then of course, you know, evaluate, right, you know, and that's it basically, right? Pass, right? So build initial state, right? It's ridiculously simple, right? And then while, right, you know, and you have some evaluation, right, of course, you know, define goal evaluation, right? That's basically, right? And of course, you probably need some global variable, basically, right? Tell percept, so while goal evaluation, basically, you know, something like this, right? And basically you keep doing it, basically, right? Query, ask query, tell action, right? And you took it, right? And basically get perception, yeah, tell get perception, right? Get perception, right? And tell perception, ask query, right? Oh, query, get perception, right? Yeah. Oh, we need also tell perception. No. So this is a little bit, but all the dirty details are there, right? So get perception, tell perception. So this goes to knowledge base, right? Knowledge. This is built by inference engine for using knowledge base, right? And then this updates world, right? Right. Let me check the goal. So yeah, so really simple pseudocode, right? Just fill in the details. How again, the magic here, right? Maybe you disagree with any of this. Maybe you think it's too simple, right? It is simple conceptually, of course, but when you see the actual logic inference, right? Means you actually need to go to normal forms and come up with truth tables, right? Not so simple at all, right? So again, to conclude, the biggest issue is not only that it's hard to use this type of logic. In general case, it's very limited because you don't. The biggest issue is with this fact here, right? This P111, right? This way of encoding knowledge is very, again, what's the word? What's the word? No, you go ahead. It's not. I'm not going to take offense.
Sorry?
Did you say what kind of? This,
I was talking to Lee.
okay, right. So this way of encoding is not so great for larger state. So you can see that encoding larger worlds would be quite a pain. We would need a stronger encoding, wider. Right. So we need some additional. So that's something for next lecture. So on Thursday, we will look at encoding the world when you have actually, basically, you could say, with arguments, I could say, maybe, right? So one, how to encode these coordinates actually as numbers, right? That'd be nice to have, right? You guys agree?
Yeah.
Okay. Many questions? I won't make you build logic inference engine yourself, right? So the issue is this again is that it theoretically works, but it becomes very quickly for a large number of facts, the inference becomes infeasible, right? Solving it, right? So this is, I wouldn't say it's dead end, because again, from this lecture we learn the word inference, right? Inference that's happening in ChatGPT, everything is doing inference, right? Trying to build the next answer, right? Next token, right? Same thing actually in a way, right? Inference is like a very important concept in AI. So that's something you take away from this today's lecture. All right. All right. So thank you. Unfortunately, these next lectures are relatively dry, so it'll be quite a challenge for me to make them spicy for students from high school. I don't know how I'll do it. It'll be pain, but I'll do it somehow. I don't know. I'll include the Wumpus again, I guess. Right. All right. So that's it for today. So see you on Thursday.
You could make a playable.
Yeah. Or even better, I'll make you make a very playable Wumpus. That's easier for me.